Hi everyone, welcome to our physics class. In the previous class, we learned about Ørsted's experiment, the magnetic effect of electric current, Ampere's swimming rule, right hand thumb rule, and some very important properties of magnetic field lines. So today we are going to discuss about the Lorentz force. So this is moving charges and magnetism part 2. Okay, well, so let's start today's class. So Lorentz force. Lorentz force means the total force acting on a charged particle. It is moving in a region where both electric and magnetic fields are present. Okay, first here let us consider the crossed electric and magnetic fields which are mutually perpendicular to each other, and charged particle is moving perpendicular to the direction of magnetic field, even perpendicular to the direction of electric field. So only in the presence of electric field, so what amount of force acting on the charged particle, that is very important. So let us consider the charged particle, that is Q. So only in the presence of electric field, in the absence of the magnetic field, the force acting on the charged particle is Fe vector. So that is QE. Is it not? The force acting on the charged particle, that is due to the electric field. The force acting on charged particle due to electric field is F vector is equal to Q into E vector. We call this as equation number 1, and the direction of the force is same as that of the direction of electric field. So here Fe vector is QE vector. Fe vector means the force acting on plus Q due to electric field. The direction of force, that is same as that of the direction of electric field, and the force here does not depend on the speed. The force acting on charged particle due to electric field does not depend on the speed of the charged particle. Okay, in the absence of electric field, only in the presence of the magnetic field. So what amount of force acting on charged particle, that is also very important. So the force on a moving charge, force acting on a moving charge plus Q. So due to the magnetic field, so this is F. Let us consider this one as F E vector. This is F B vector. So that is equal to Q of V vector cross B vector. So call this as equation number 2. So actually this is Lorentz electric force and this is Lorentz magnetic force. So this is the mathematical expression for force acting on a moving charge plus Q due to the magnetic field. So this is a force acting on charged particle due to electric field. So Lorentz force means the total force acting on charged particle. Total force acting on a charged particle moving in a region where both electric and magnetic fields are present. Only in the presence of electric field, the force acting on charged particle, that is QE vector, that is moving vertically upwards, that is along positive y-axis. So only in the presence of magnetic field, the force acting on charged particle is FB vector, that is moving vertically downwards, that is along negative y-axis. Actually, that direction can be determined by using Fleming's left hand rule. So this is the Fleming's left hand rule. Stretch out the first three fingers. Stretch out the first three fingers of left hand. First three fingers of left hand in three mutually perpendicular directions. Three mutually perpendicular directions. Angle between F vector and B vector is 90 degree. V vector and D vector is also 90 degree. Stretch out the first three fingers of left hand in three mutually perpendicular directions. Then the four-finger points. What is this? Four-finger. Four-finger points in the direction of the magnetic field. The middle finger points the direction of the motion of charged particle. Thumb points in the direction of Lorentz magnetic force. So let us apply this rule to find the force acting on plus Q due to magnetic field. So the force acting on plus Q due to magnetic field, so that is here vertically downwards, that is along the negative y axis. So what is the statement of Fleming's left hand rule? Let's stretch out the first three fingers of left hand in three mutually perpendicular directions. Three mutually perpendicular directions. Four finger points in the direction of magnetic field. Middle finger points in the direction of motion of charged particle. Thumb points in the direction of Lorentz magnetic force. So what is the meaning of Lorentz force? The Lorentz force means the total force acting on a charged particle moving in a region where both electric and magnetic fields are present. So the mathematical expression for the Lorentz force. Lorentz force is F vector is equal to F E vector plus F B vector. So F vector is equal to Q E vector plus Q of V vector cross B vector. So this is the mathematical expression for the Lorentz force. F vector is equal to QE vector plus Q of V vector cross B vector. This is the force acting on charged particle due to the electric field. This is Lorentz electric force, and this is the force acting on charged particle due to the magnetic field. So that is FB vector is equal to Q of V vector cross B vector, and this is the total force acting on charged particle. Total force acting on charged particle due to electric field and the magnetic field. So what is the meaning of Lorentz force? Lorentz force means the total force acting on a charged particle. Total force acting on a charged particle moving in a region where both electric and magnetic fields are present. So this statement is very, very important. So what is the meaning of Lorentz force? The total force acting on a charged particle moving in a region where both electric and magnetic fields are present. So this is Fleming's left hand rule. So what is the statement of Fleming's left hand rule? Stretch out the first three fingers of left hand in three mutually perpendicular directions. Forefinger points in the direction of magnetic field. Middle finger points in the direction of motion of charged particle. Thumb points in the direction of Lorentz magnetic force. Okay, so the next topic, that is velocity selector. So this is again the crossed electric and magnetic fields. So let us consider the crossed electric and magnetic fields. So electric field and magnetic field, which are mutually perpendicular to each other, and a charged particle that is moving, a charged particle plus q that is moving along the positive x axis. So the force acting on charged particle due to electric field. So the force acting on charged particle due to the electric field. So the mathematical expression, that is F E vector is equal to Q E vector. So this can also be written in the form of F E vector is equal to Q E into J cap. So E is the magnitude of E vector, J cap is a unit vector, indicates the direction of E vector, that is along positive y-axis. What is the meaning of unit vector? So vector having unit magnitude. Okay, J cap is a unit vector. Its magnitude is 1, indicates the direction of E vector, that is along here positive y axis. The direction of electric field, even direction of force, both are same. And the force acting on the moving charge, force acting on the moving charge q, moving charge q due to the magnetic field, that is F B vector is equal to Q of V vector cross B vector. Okay, so first here let us consider E vector is equal to E into J cap. So this is along positive y-axis and V vector is V into I cap. So V is the magnitude of velocity of the charged particle. I cap indicates a direction of velocity, that is along positive x axis, and B vector is B into K cap. B is the magnitude of the magnetic field. K cap indicates the direction of the magnetic field. So what is the direction of magnetic field? That is along positive z axis. So K cap indicates the direction of the magnetic field, that is along positive z axis. So K cap is a unit vector, its magnitude is 1. So now this equation can also be written in the form of FB vector is equal to Q of V vector that can be written in the form of V into I cap, right? V vector is V into I cap cross B vector is B into K cap. B into K cap. So FB vector is equal to Q of QVB. So VB or scalars, that is taken as outside. The remaining is I cap cross K cap, right? So I cross J means K cap. J cross K means I cap. So I cross K, that is minus J, right? So this is a property of cross vectors Q, V, B. So what is the value of I cap cross K cap? So K cap cross I cap is J cap. I cap cross K cap, that is minus J cap. So this is a property of vector product, right? So the magnitude of F E vector is QE, that is just F E, that value is QE. So call this as equation number 1. So call this as equation number 2. Okay. So the magnitude of FB vector, that is QVB. The magnitude of minus J cap is 1. So FB is equal to QVB. So call this as equation number 3 and call this as equation number 4. Okay, right? So this is the force acting on charged particle. So that is plus Q due to electric field, that is along positive y-axis, and this is the magnitude of force acting on charged particle, that is QE. And this is the force acting on charged particle due to the magnetic field. So this direction can be determined by using Fleming's left hand rule. So FB vector, that is along negative y-axis. Okay, so FE vector, that is along positive y-axis, FB vector, that is along negative y-axis. The direction of FB vector that can be determined by using the Fleming's left hand rule. The direction of FE vector, that is same as that of the direction of electric field. So this is the magnitude of the force acting on charged particle due to the magnetic field, that is QVB. Suppose here the magnitude of FE vector, is more than the magnitude of FB vector. The magnitude of FE vector is more than the magnitude of FB vector. So what is the net force acting on charged particle? Net force acting on charged particle, that is FE minus FB. Is it right? Suppose if the magnitude of FB vector is more than the magnitude of FE vector, so in this case the net force acting on charged particle is FB minus FE. Suppose if the magnitude of FE vector, that is equal to the magnitude of FB vector. So this point is very, very important here. So here, by adjusting the electric field and magnetic field, by adjusting the electric field and magnetic field until the net force acting on charged particle is zero. So Fe vector magnitude, that is equal to magnitude of Fb vector. So what is the net force acting on charged particle? So that is Fe minus Fb. Both are equal. Get cancels. That is equal to zero. Okay. Electric field strength is more than the magnetic field strength. In that case, the magnitude of Fe vector is more than the magnitude of Fb vector. Okay, so in this case, if a charged particle enters the presence of both the electric and magnetic field, so the net force acting on charged particle is Fe minus Fb, that is moving along the positive y-axis, because here electric field strength is much stronger. Suppose if a charged particle enters in the presence of both electric and magnetic field, but the magnetic field strength is much stronger as compared to the electric field strength, the net force acting on the charged particle is Fb minus Fe. So the charged particle is moving vertically downwards, right? So if a charged particle enters in the presence of both electric and magnetic field, the electric field strength and magnetic field strength both are equal. So Fe is equal to Fb. So then the charged particle is moving along the same direction. It does not experience any force. So in this case, Fe is equal to Fb. That means QE value, that is exactly equal to QVB. Is it not? So by using this formula, we can easily calculate the value of V. So here Q get cancels. V is equal to E divided by B. So this is the mathematical expression for the velocity selector. The ratio of electric field to the magnetic field. The ratio of electric field to the magnetic field, so is called the velocity selector. So this arrangement is used for selecting charged particles of same velocity from beam of particles moving with different velocity. Okay, so what is the meaning of velocity selector? By selecting, okay, velocity selector means by selecting the charged particles. By selecting what? Charged particles of same velocity from a beam of charged particles moving with different velocity. Okay. Now look at this animation. So actually here the charged particle is moving in the presence of both electric and magnetic field. So actually here cross marks indicates the perpendicular magnetic field. So that is directed into the plane. Okay. So cross mark indicates perpendicular magnetic field that is directed into the plane. So these are the two charged metallic sheets. So upper one is positively charged, lower one is negatively charged, and there is a uniform electric field set up in between the two plates. Okay, so but here the magnitude of the force acting on the charged particle Fe that is exactly equal to the magnitude of force acting on charged particle due to the magnetic field. So the magnitude of force acting on a charged particle due to electric field, that is exactly equal to the magnitude of force acting on charged particle due to the magnetic field. So that is why the net force acting on this charged particle is zero. So what is the net force acting on a charged particle? So that is F is equal to Fe minus Fb. So Fe is QE. Okay. So Fe is QE, Fb is QVB. Both are equal and opposite, get cancels, that is equal to 0. So here QVB. So this is QVB, force acting on charged particle due to the magnetic field. So acts vertically upwards. So this is the force acting on charged particle due to electric field, acts vertically downwards. But here both force acting on charged particle due to magnetic field, force acting on charged particle due to electric field, both are equal but quite opposite. So what is the net force acting on the charged particle? In this case, that is 0. Okay, so that is why the charged particle is here moving along the positive x-axis, right? Okay, so the next topic, the force on a charged particle moving in magnetic field. Force acting on a charged particle moving in a magnetic field. Okay, so what is the expression for force acting on a charged particle moving in the presence of the magnetic field? That is force acting on a charged particle Q, that is due to the magnetic field. It is given by Lorenz. So it is given by F B vector is equal to Q of V vector cross B vector. So the direction of this force, so that can be determined by using right hand corkscrew rule. So look at this diagram. Actually your FB vector is perpendicular to plane containing two rotational vectors, that is V vector and B vector. Okay, but V vector does not lie along x-axis, does not lie along y-axis. That is why V vector that should be splits into the two rectangular components. Okay, so here we have to imagine a rectangle. So this is the angle theta. Theta is the angle made by V vector and B vector. So this is perpendicular, hypotenuse. This one is base. So the base component of V vector is V cos theta. V cos theta, that is along the direction of magnetic field. And this is V sin theta, that is perpendicular to B vector and perpendicular to F vector. Okay, so here the force acting on the charged particle, the force acting on the charged particle is, so this is actually the magnitude of the force, magnitude of force acting on charged particle due to the magnetic field. So what is the meaning of cross product of two vectors? So the magnitude of cross product of two vectors is V B sine theta. Cross product of two vectors is a vector. Cross product of two vectors is a vector. So its magnitude is given by the product of magnitude of two vectors and sine of the smaller angle in between them. That means in between V vector and B vector. Okay. So the direction of this force that can be calculated, so that can be determined by using a rule, that is the right hand corkscrew rule. The right handed corkscrew is turned such that the tip of the screw moves towards the direction of force. The head of the screw turned, that gives the direction of rotational vectors. Okay. So this is the direction of force that is perpendicular to a plane. F vector is perpendicular to a plane containing the two rotational vectors. Those are V vector and B vector. So if V cross B, the force is vertically upwards. Suppose the rotational vectors are B cross V. B vector cross V vector, then F vector is moving vertically downwards. Okay. Suppose if the magnetic field that is perpendicular to the direction of motion of charge particle. Okay, so this is the direction of magnetic field that is along positive y-axis. Okay, so this is the direction of motion of charge particle, so which are mutually perpendicular to each other. So then what is the direction of force? Direction of force acting, that is along positive z-axis. Okay, this is the direction of force, that is F B vector is equal to Q of V vector cross B vector. Okay, so that is Q V B, Q V B sine, what is the angle between V vector and B vector? That is 90 degree. So sine 90 is 1. So the force acting on charged particle is maximum in this case, that is QVB. Okay. So the direction of force acting on charged particle. So here that can be determined by using the Fleming's left hand rule. Stretch out the first three fingers of left hand in three mutually perpendicular directions. So forefinger points in the direction of magnetic field, the middle finger points in the direction of motion of charged particle, thumb points in the direction of force acting on charged particle. So that is along here positive z-axis. So the next topic is motion of a charged particle in a uniform magnetic field. So what is the expression for the force acting on a charged particle in the presence of uniform magnetic field? So that is F vector is equal to Q of V vector cross B vector. The force acting on the charged particle due to the magnetic field, that is given by FB vector is equal to Q of V vector cross B vector. So the magnitude of this force is FB is equal to QVB sine theta. So theta is the angle made by V vector and B vector. The velocity of the charged particle parallel to the direction of magnetic field. That means here V vector is parallel to the direction of magnetic field. So what is the value of theta? Theta is equal to 0 degree. Even so in this case the force acting on charged particle is QVB sine 0. QVB sine 0. Sine 0 is 0, 0 and anything is 0. So the force acting on charged particle is 0. Even the velocity, the motion of charged particle is anti-parallel to the direction of magnetic field. So then what is the value of theta? Theta is equal to 180 degree. If V vector is anti-parallel to B vector, then theta is equal to 180 degree. The force acting on charged particle F is equal to QVB sine 180. Sine 180 is 0. Again 0 and anything is 0. Okay. So if a charged particle is moving parallel or anti-parallel to the direction of magnetic field, it doesn't experience any force. If a charged particle is perpendicular to the direction of magnetic field, so it will experiences maximum force, that is QVB sine 90, that is QVB. So look at this animation. So if V vector is parallel to B vector, force is 0. V vector is perpendicular to B vector. V vector is perpendicular to B vector. The force acting on charged particle is maximum. If V vector is parallel to B vector, V vector is parallel to B vector, the force is 0. Okay. So the next special case, when the initial velocity of the charged particle is perpendicular to the direction of magnetic field. Charged particle in a transverse magnetic field. So when the initial velocity of the charged particle is perpendicular to the direction of magnetic field, so charged particle in a transverse magnetic field. So this is a charged particle. If it enters a perpendicular uniform magnetic field, so magnetic field lines here directed into the plane. Okay, so that is normally inverse. Direction of magnetic field is normally inverse. So charged particle enters the perpendicular uniform magnetic field. So immediately the charged particle describes circular path. Charged particle describes the circular. Charged particle describes the circular path. If a charged particle enters a uniform magnetic field, parallel or anti-parallel to the direction of magnetic field, it doesn't experience any force. So the nature of trajectory of charged particle is a straight line. That is a linear path. That is the previous case. So if a charged particle enters parallel magnetic field. So what is the nature of trajectory? This point is very, very important. That is straight line or linear path. Charged particle enters a parallel magnetic field. That means charge particle enters a uniform magnetic field. So charge particle is moving with velocity v vector. So that is parallel to the direction of the magnetic field. So if theta is equal to 0 degree, so the nature of trajectory of charge particle is straight. Or if a charge particle enters a uniform magnetic field with velocity v vector, that is moving anti-parallel to the direction of magnetic field. So in this case, theta is equal to 180 degree. So in this case, charge particle does not experience any force. So again, here the nature of trajectory of charge particle is straight. But here a charge particle enters a perpendicular uniform magnetic field. So immediately the charge particle describes the circular path. Okay, so the force acting on charge particle is maximum. The direction of force acting on charge particle, so that can be determined by using the Fleming's left hand rule. Stretch out the first three fingers of left hand in three mutually perpendicular directions. So the forefinger points the direction of magnetic field, that is normally inwards. The middle finger points the direction of the motion of charge particle, that is vertically upwards, and thumb points the direction of force acting on charge particle, that is along the radius towards center. Okay, stretch out the first three fingers of left hand in three mutually perpendicular directions. Okay, forefinger points in the direction of magnetic field. Here, direction of magnetic field is normally inverse, that is directed into the plane. Okay, so the middle finger points the direction of motion of charge particle, that is vertically upwards. Thumb points the direction of force acting on charge particle, that is along the radius towards center. So that is actually Lorentz magnetic force. What is the mathematical expression for Lorentz magnetic force? That is QVB. Okay, so if a charge particle enters a perpendicular uniform magnetic field, so what happens? Charge particle describes the circular path. Okay, so here the centripetal force, whatever the particle, if it is moving along the circular path, so here the charge particle is moving along the circular path. If a charge particle moving along circular path, it must requires a centripetal force. Okay, the charge particle is moving along circular path, it must requires centripetal force, that is actually here provided by the Lorentz magnetic force. That means centripetal force, that is exactly equal to the Lorentz magnetic force, right? So what is the mathematical expression for centripetal force? That is mv square divided by r, that is equal to fb, that is qvb. So 1v get cancels. The radius of this circular orbit, that is equal to mv, r is equal to mv divided by qb. So this is a very, very important mathematical expression. So what is this? Expression for radius of circular orbit. Okay, r is equal to mv divided by qb. And what is the time period? Time period of the charge particle. So speed is distance divided by time taken for one complete rotation of charge particle. The total distance traveled for one complete rotation is 2 pi r. The time taken to complete one rotation is time period. So V is equal to 2 pi r divided by t. So t is equal to 2 pi r divided by V. Okay, so what is the value of r? 2 pi divided by v. R value is mv divided by qb. So v get cancels. So the mathematical expression for time period is t is equal to 2 pi m 2 pi m divided by qb. So this is the mathematical expression for time period of charged particle. Okay, so what is the meaning of time period? Time taken by the charged particle to complete one rotation in the presence of perpendicular uniform magnetic field. So how does the time period of charged particle depends on the speed and radius. So this point is very important. Actually here the mathematical expression for radius r is equal to mv divided by qb. So r is called gyro radius, that is also called cyclotron radius. Gyro radius or cyclotron radius. Okay. So the time period of how does the time period of charged particle depends on the radius and the speed. This point is very important. So look at this mathematical expression. T is equal to 2 pi m divided by cubic. That means the time period of charged particle does not depend on the radius and even speed. That means if a charged particle to complete one rotation in a very small circle and a very large circle in the presence of perpendicular magnetic field is same, because the time period does not depends on the radius, does not depend on the speed. So that means the time taken by the charged particle to complete one rotation in the presence of perpendicular magnetic field in a very small circle and in a very large circle in the presence of perpendicular magnetic field, that is same, right? So even the frequency. So what is the meaning of frequency? Frequency means number of revolutions per second made by charged particle. Okay, so that is actually reciprocal of time period, that is qb divided by 2 pi m. Okay, so this is the mathematical expression for time period. This is the mathematical expression for frequency. What is the meaning of frequency? The frequency of charged particle means number of revolutions per second made by charged particle. Actually this is called the cyclotron frequency. So this is cyclotron frequency. Okay, so even frequency of charged particle also does not depends on the radius of the circular orbit and the speed of charged particle. Actually, this is the principle of cyclotron. Cyclotron is a device that is used to accelerate the positively charged particles. Okay, so time period of charged particle does not depends on the radius of circular orbit and the speed of charged particle. Even the frequency of charged particle also does not depend on radius and the speed of the circular orbit. Okay. The next special case. So that is the motion of charged particle entering a uniform magnetic field in any direction. Okay, charged particle enters a uniform magnetic field in any direction. So look at this diagram. So this is the charged particle. So enters the parallel magnetic field, that means uniform magnetic field in any direction. So this is the direction of the velocity. So this is the direction of the velocity of the charged particle. A tangent drawn at any point so gives the direction. So here the velocity of the charged particle is not parallel to the direction of magnetic field. If it is parallel, it doesn't experience any force. The nature of trajectory of charged particle is a straight line. Is it not? If v vector is parallel to b vector, the angle in between them is zero. The force acting on the charged particle is zero. That means the nature of trajectory of charged particle is a straight line. Suppose if v vector is anti-parallel to b vector, theta is equal to 180 degree. Again, the charged particle does not experience any force. So again, the nature of trajectory is straight line. If v vector is perpendicular to b vector, the charged particle describes the circular path. The force acting on charged particle is maximum, that is qvb. But here the velocity of charged particle is not parallel, not anti-parallel, not perpendicular to the direction of magnetic field. So this is the direction of velocity. So making an angle theta with the direction of the magnetic field. So this is the direction of velocity. So this is so this is the angle theta. So theta is angle made by direction of velocity of charged particle and direction of magnetic field. So if a vector does not lie along x and y direction, so that vector should be split into two rectangular components. Is it not? So here we have to imagine a rectangle. Okay, so this is perpendicular. What is this? Perpendicular. This one is hypotenuse. This one is base. This is the parallel component of velocity. So your v vector is splits into two rectangular components. One is the parallel component and another one is the perpendicular component of velocity. Okay, so what is this? Perpendicular. This one is hypotenuse. This one is base. Base component is v cos theta. Okay, and what is this? Perpendicular component. Perpendicular component of velocity is v sin theta. So here the function of v cos theta and v sin theta. So that is very, very important. Actually, the parallel component of velocity make the charged particle moves along the direction of magnetic field. So parallel component of velocity make the charged particle move along the direction of magnetic field, but the perpendicular component of velocity make the charged particle move in a circular path. Is it not? The perpendicular velocity make the charged particle move in circular path. Parallel component of velocity make the charged particle move along the direction of magnetic field. So the resultant of these two motions cause the particle to take a spiral path. So this point is very, very important. Okay, so here v vector, the velocity of charged particle, that is splits into two rectangular components, parallel component and perpendicular component. So parallel component of velocity make the charged particle move along the direction of magnetic field. The perpendicular component of velocity make the charged particle move in circular path, the resultant of these two motions, the resultant of these two motions cause the particle to take a spiral path or helical path. So, what is the nature of trajectory of charged particle? If it enters uniform magnetic field in any direction, that is helical path or spiral path. If a charged particle enters uniform magnetic field parallel to the direction of magnetic field, nature of trajectory of charged particle is a straight line. If a charged particle enters a uniform magnetic field anti-parallel to the direction of magnetic field, nature of trajectory of charged particle is a straight line. If a charged particle enters a uniform magnetic field that is perpendicular to the direction of magnetic field, so in that case, charged particle describes the circular path. If a charged particle enters a uniform magnetic field in any direction with the magnetic field, the charged particle describes helical path or the spiral path. So that is the nature of trajectory of charged particle. So the functions of parallel component of velocity and perpendicular component of velocity, that is very important here. So if a particle moving along a circular path, it requires centripetal force. Okay, actually here perpendicular component of velocity make the charged particle move in circular path. That means the centripetal force m, so v perpendicular square divided by r is equal to q v perpendicular b. The perpendicular component of velocity v perpendicular get cancels, so r is equal to mv perpendicular divided by qb. Okay, so time period is t is equal to 2 pi r divided by v, so r divided by v perpendicular, so that is m divided by qb, so 2 pi m divided by qb. So this is the time period of charged particle to complete one rotation in spiral path. Okay, so again time period does not depends on radius and speed. Even the frequency also does not depends on speed and radius. The frequency expression is qb divided by 2 pi m. So this is the frequency of charged particle. So this is the time period of charged particle. Okay. So time period of charged particle does not depends on the speed and the radius. So this is for the perpendicular component of velocity. So this is actually called the pitch of helix. So during time period t, so the horizontal distance covered by charged particle. So for one complete rotation in spiral path, so this is a charged particle. So after one complete rotation, so this is the location of the charged particle, right? So the horizontal distance covered by charged particle during the time capital T. So actually that is called the pitch of helix. So the parallel component of velocity is distance. Actually here distance is pitch. Time taken is capital T. So the mathematical expression for pitch of helix. This is very important mathematical expression. So pitch of helix is equal to parallel component of velocity into time period. What is the meaning of pitch of helix? That is just the distance traveled by a charged particle during the time interval, that is capital T. So parallel component is v cos theta, time period is 2 pi m divided by qb. So 2 pi m divided by QB, so into V cos theta. So this is the mathematical expression for pitch of pitch of helix. Okay, so when a charged particle enters a uniform magnetic field parallel to the direction of magnetic field. In that case, nature of trajectory is a straight line. So if a charged particle enters a uniform magnetic field anti-parallel to the direction of magnetic field, nature of trajectory is a straight line. If a charged particle enters a uniform magnetic field perpendicular to the direction of magnetic field, so in that case, charged particle describes a circular path. So the nature of trajectory of charged particle is circle. If a charged particle enters a uniform magnetic field in any direction with magnetic field. So look at this animation. The charged particle enters a uniform magnetic field in any direction. The charged particle describes a spiral path or helical path. Okay, so these mathematical expressions are very, very important. So especially pitch of helix mathematical expression is very important. That is 2 pi m divided by qb into v cos theta. What is the meaning of pitch of helix? During the time interval capital T, the distance traveled by a charged particle. The distance traveled by a charged particle during the time capital T. Okay, so that is called the pitch of helix. Okay, so even in spiral path, the time period and frequency does not depends on the radius of the spiral path and the speed of the charged particle. Okay, thank you.